my fat head up here. Sorry. Okay. All right. So we're going into polynomials, and then I warned you, like that, that silly worksheets that we gave you here, factoring and multiplying is coming up. Well, it's probably not going to come up till Wednesday. What we really have to talk about is the graphing of polynomials and some stuff, attributes. Had a big, robust plan today, and you have 7 pages in front of you of notes. We're going to get through like 4 of them, and I'm going to skip around still, and it'll still be a full, chock full of, the whole period almost. So you're really going to have to pay attention here. Okay, so the first function here is just linear. Okay, so this is really just y equals x. And that's what this is a picture of, because the slope is 1, right? Rise 1, run 1, rise 1, run 1. So, and then the y-intercept is 0. So if you remember y equals mx plus b, this is y equals 1x plus 0. And then b is the y-intercept. Hopefully you remember that. But really it's the breakdown of things that when we get the polynomial is what you need to know, like domain and range and behavior. I like to use my fingers for this. Turn this so you can see a double notes here, both on the screen and here. And hopefully you can see me as I go over here. Okay, maybe not. It's probably not my head. My head's in the way again, but X finger, Y finger. Input, say it. That's how we graphed everything in the beginning of the year. Did you hear them? Wow, that was nice. So as I input these X's, as I get bigger for X, what happens to the Y's? They get bigger. That's where this as X goes to infinity, so does Y. And then as I plug in negative X's, what happens to the Y's? They get smaller. They get more negative. So that's where as X goes to negative infinity, so does Y. We are actually going to use different different notation for this. We're going to use what's called limit notation and write this down over there. Do this a little different order than last hour. What that means is the limit of f of x is, limit does mean approaching. And that's what I just want you to know. So it does mean as x approaches, what does y? So the limit of f of x as x approaches negative infinity, I'm going to move my arrow, and I'll move my body. I see people sitting over here that are leaning to try to see this. Equals negative infinity. This actually is the same as saying this. Okay? Just limit notation, and that's what we're going to get to there. So limit notation means as y approaches, limit of f of x, as y, f of x is y, as x approaches negative infinity, what does y approach? All right, and that's kind of, I wanted to reverse what I was saying on that. Critical points, not really a big deal, just input output. But 0, 0 is actually the most critical point, the y and x intercept for this one. Then it gets real important that 0, 0 is a critical point for the absolute value function, which we did do this year, right? Do you remember that? The v. All right, and we did actually call 0, 0 kind of like a vertex, similar to a parabola. Oh, and then we're getting to a parabola. Whew, that's when things were a little rough back in the day with those parabolas and what I saw for work there when we were in school and out of school and so on and so forth. So hopefully we can pick this stuff up. But back to absolute values, notice the range. Range is a little bit different. And then take note that we have a bracket on that 0. That means 0 is part of the range and then everything above that. But the graph doesn't exist down here. There are no y values on the negative side. So that's why the range is limited there. Now the end behavior, again, I'm not going to write the limit notation. We should know that we can change that to that. But as I get bigger for x, of course, I'm getting bigger for y, input, output. But as I get negative for x, the y's do go off to positive infinity. So that is a little difference there compared to the linear function. All right, and then don't really call those critical points. Those are just other input outputs, negative 1, 0, and 1, 0. And then here's your quadratic. Oh, and I forgot to note something. Even, odd. I'll go back to that. And I think I did talk about that in the first semester. If not, let's treat it as brand new. Same thing though, range limited. This is a vertex, so I really would call this a critical point. The vertex for the parabola, that's what we want to know, where things are located. Then the end behavior is similar to the absolute value, so I don't have to cover that again. Now I'm going to go to the cubic. And actually, I did have my class do this last hour. We're going to go to the graphing calculator. So I accidentally hit that. If you have one, there's your pictures. My bad, dogs. Roof. But I'm freaking out now. Okay, that's what I wanted to go. Okay, you can sue me. I just put your pictures on YouTube. All right, go for it. I have no money. All right. So just so you know that the y equals exists, hit y equals. All right. So that's just this is why it's called a graphing calculator, the ability to graph. And in the notes I reference a Desmos activity, but we won't be able to get to it. If you have a chance when you're doing some of your homework, you want to type the equation in the y equals and see the graph and see what you have on your grid and see that they match, you can do that. It's up to you. You don't really have to. But y equals, put x caret delicious cubed, and then go ahead and look at the picture. And we could have gotten this graph input output anyway, right? And we are going to input output. So there's the picture of an x cubed. But input outputting, let's just go ahead and do that mentally here and put the picture over here. And when I plug in 0 for x, what do I get for y? 0. No one said a word. All right. When I plug in 1 for x, what do I get for y? 1. Good. I got somebody. When I plug in 2 for x, careful, what do I get for y? What's 2 cubed? 8 is correct. Not 6. No one said 6, but sometimes people accidentally add instead of multiply. So 2 comma 8, I believe I went 8 up. And then what's negative 1 cubed? That's actually a negative 1. A negative times a negative times a negative. That's 3 negatives. 2 cancel and 1's left over. And then negative 2 cubed, 5, 6, 7, 8. And hopefully you remember a sound that I used. Okay, but first of all, okay, so here's the sound. Now let's go back to even and odd. Do you remember the sound? Let's go to even. They call this function an even. That's weird. Why? Do you remember this? What is that the sound for? Starts with an S. S-Y. S-Y-M-M. I have no time. Symmetry. And what this has is y-axis symmetry. And then I'm going to be honest, why the word even for that? It does come from polynomials, right? But not only are some polynomials even. There's many different functions. This is not even as far as the degree on this polynomial. So that's where we got to be careful with that word even. But I think that's where the word comes from polynomial land. X squared is even as a degree. And lo and behold, this is an even function. It's a y-axis symmetry scenario. And there's other attributes, so on and so forth. Now, what's weird is they called this one odd. Well, is it just because it's y equals x to the first, and that's an odd degree? Maybe that's where the name originated, but it's more than that. Ooh, that's weird. What is that symmetric with respect to? What is this point right there? The origin. So odd functions have symmetry about the origin. And those you can lock in. So that might be a new thing for you. I don't know if we talked about even and odd functions. Okay, so yeah, I've asked calculus teachers, why is it so important that I know a function's even or odd? And there's some minor things, I guess. So I guess it's a thing. So what do we think this cubic is? Well, let's do the music. What kind of symmetry is that? Odd. Okay, so this is origin. We really should have said origin, but that means odd. Okay, origin symmetry means it's an odd function. And then lo and behold, it's x to the third, which is an odd power. But be careful. There's more than just polynomials with odd degree, it being an odd function. There's other odd functions that are not polynomials. Domain and range, all real numbers again. Guess I'm sticking with green. So a lot of attributes, not hard, but different. And then we're going to put this in limit notation. So what's the limit of y, what does y approach? That's what that first thing that I wrote there actually says, as x approaches negative infinity. And we'll go to that right away. A new notation for you. Well, X finger, Y finger, or X pen, as I plug in these X's, this is where the Y's go. So it does go off to negative infinity as I plug in negatives for X. And then the limit of Y, what does Y approach? As X approaches infinity. And that is infinity. Okay? What are the critical points? I would just say 0, 0. That's actually a point called a point of inflection. You notice how it flattens out there? Do you notice that? Right? And when we see our next graphs, we want to know where that point is, where that flattens out. Okay, so blah, 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 blah. We're going to get bigger. Actually, tomorrow we're going to go on and go up to x to the fourth, fifth, sixth, and beyond and see those end behaviors and what happens. Okay, and then this is a random spot here that I need some space. So I'm going to put some real tiny graphs right here because this is the section for extrema. And actually, you have some extrema up at the top of those pictures, like the absolute value, for instance. I'm going to put that right here. So here's this absolute value function again. I could go up to that one and just use that picture, but that low point right there, if you look at some of the terms in that sentence, that low point is absolutely the minimum point for this graph, right? Okay, there was no lower y. So this is an absolute minimum, meaning that is absolutely the lowest y coordinate of this function. So that's an absolute min. I don't have this picture up there, but imagine a parabola that's going down. And I will put it at the origin for the vertex. Well, if you have a parabola going down, then this is absolute maximum. There is absolutely positively no higher y coordinate. And do notice that the word min and max are describing the y's. All right? And that's something important when we talk about how do we note these things. Yeehaw. I'm going to cowboy that one over here. All right? And then imagine in the future you have an x cubed, which you will see today. We're actually going to input, output, and graph and see this happen. I think I made a little mistake in last hour with one of my points. It's okay when we get to the graphing. I'll try to make a note of it. But okay, so now notice this one. Is this absolutely the highest point of the whole graph? Yes or no? No. So that's a relative. What does relative mean? Or local. Use that term last hour. Local or relative. Relatively speaking, that's a condition. That's like hey, relatively speaking, that like kind of limits the, and you're talking about just in relative to this little scenario. Well, this is a relative minimum relative to this little area of the graph and not looking at other areas of it. Or locally speaking, this is the relative maximum. And this is the relative or local minimum because there is a lower point than that in the graph overall. Okay? So local and absolute, understanding those two things. All right. This is why this is a different scenario. Hey, looking at the linear function, what kind of slope is this, positive or negative? Positive. So this has a leading coefficient that is positive. The graph of this looks like it's y equals 2x. I think that's what it looks like. It looks like it's approximately a slope of 2 with a y-intercept of 0. Leading coefficient is positive. That's because there's a positive slope. What's the next one? Negative. Actually, the equation of this one, best matching this, would be negative 1/2 x plus 1, because it does have a y-intercept of 1, right? Right? So that would be the actual equation from that. Hopefully you remember that from last year in grade school. All right, but the point of this is it's a negative leading coefficient. This one's positive. What about letter C? Negative or positive? Negative. Next one. That's the only way it could work. It's all about the end behavior. You really should be focusing on this and this. It really is. Okay, it's how it ends to the right. We read graphs left to right, by the way. All right, so that's really the key on this. So then the next ones, what do you think of these cubics? What is letter A, positive or negative leading coefficient? That's a positive. It's because it ends positive, and you will see this as you do your situations. What about this one? Negative. What about this one? It's really all you got to look at. What about that one? And there's a little curly Q in the middle. That's not an x cubed. That's there's more. That's at least an x to the fifth, and that's what you're going to find out about those little waves in there. At least it could be more, depending on the picture. Okay, so I think I can give you a minute to actually do these, but you know what? I'm taping live and I can't pause my situation. So let's just kind of go through it, and hopefully you can talk more than second hour. I caught someone sleeping. I had to scare the heck out of him. Hey, and he was ah! All right. So anyway, but not exciting, but it's pretty easy. Sign of leading coefficient, positive or negative. Let's be lazy. Negative. Okay, let's not even write the word. Domain and range. Anything special here? Nope. So it's all of it. Range goes from, you see it go off to infinity and negative infinity, both directions. I guess that's the best way I could explain it. Okay, now this is important. Relative maximum and minimums. Okay, so here's a max, and they are relative, so that is good. That's already stated. And there's a min. Let's start with the max. It's listed first. Careful. Okay, don't write anything yet. You don't just write a coordinate. It's very, very picky. But the word maximum is the y. So what is the maximum? What number is that? It's 6. So you say 6 located at, what's the x coordinate? Located at x equals 0. That's how you word it. So the maximum's not 0. All right, that's the x coordinate where it's located. 0, 6. 6 is the maximum when 0 is plugged in for x. So located at x equals 0. Input, say it. Output, it's an input output answer. 1, 2, 3, 4. Sorry, I was doing that. -1 located at x equals -4. Now, I haven't done this. So this is kind of brand new, but it is pretty easy. What would you describe this yellow graph as, increasing or decreasing? You read left to right, so you're correct. It's decreasing. When I read left to right, my hand goes down. When I read left to right, what is my hand doing here from this position? Decreasing. What's my hand doing here? And I'm doing that on purpose, a different color. Increasing. Now, be careful. The word increasing and decreasing, let's go to the decrease first, is describing what the y is doing. So you never use the y values as the interval. The interval is the x values that create the decreasing y behavior. I'll say that one more time. The interval in which this is decreasing is the x's that create the decreasing y behavior. So what x's do I plug in to get that first chunk? From negative infinity to, is it -4 or -1? What do you think I'm going to put? It's -4. It's the x coordinate or the x that you plugged in. Those x's plugged in order create decreasing y behavior. That's why it's done this way. And then the next one is I plugged in 0 to infinity to create that other yellow portion. All right? Not 6. You don't put 6 there. And then it's these two together here. And you might ask why I just showed you brackets on a domain and range question. A range had a bracket. Why not brackets, or why is it parentheses or brackets when you're doing increasing and decreasing? One book, our cat book, Meow, actually used brackets in an older version, 2008, I think that was published. But then it really should be parentheses, and most other books parentheses, because at these positions there's a change. So you should never really include that actual value, in that sense. So I don't know if anyone was thinking about that. I don't think I'll be a real big jerk about brackets accidentally being used there because I've seen it both ways. Right, and then the x-intercepts, I hope you really can see these pretty easily. -5, but it's -5 comma 0, right? And it's -3 comma 0. That's how these are as coordinates. And then this is 2 comma 0. Then the y-intercept will be important tomorrow. And it actually just happens to be at the maximum as well. That's just a quinky dink. All right, and then the end behavior is hopefully easy at this point. Just get used to this notation. What is y approach as x approaches negative infinity? Yet again, that's what that means and says. What is y approach as x approaches positive infinity? I did that wrong, didn't I? Boom. All right, and as x approaches positive infinity, you get a negative infinity. Yep, so as we go to negative infinity, x is actually positive infinity. You don't need to write the big fat positive there, just infinity. But I had to make a change because I made a little accident there. I don't think we have to do this one. Okay, well, actually, sorry, I thought it was going to be another one of those. I forgot, but I don't think I'm doing this whole chart. In fact, I'm not. All right, I'm probably only going to do 2 of these. It's a nice little, it'd probably be a nice little homework scenario to try to find this. It's like a little mystery. What number has this one attribute? So let's look at the first one. Looking at the graph below, what number has -5, 0, 3, 0, and 7, 0 as x-intercepts? Okay, which one? Number 1, 2, 3, 4, 5, 6. Which one is it? Number 1. We just happen to have number 1 as our possibility there. So I'm going to shrink this down and then break this down further. I got to get rid of this. There we go. So this one is and only is number 1 that has this. Now we're going to break this down and what are the other things? When I look at that picture, doesn't it look like it's a decimal? Like 0, comma, negative, like 5.5. Okay, so we'll kind of say that. And then the relative maximum looks a little bit off, like 5.2 or something. I don't know. So it is at 2 at x equals 5.2. So that's how we write that real short in there. Doesn't it look like it's a little bit off? It's not right at 5, right? So we'll do the best we can. And then the minimum looks like it's at -1.7, right? And it looks like that's a decimal again, like x equals -1.8 maybe. And then that dictates the increasing and the decreasing behavior. So decreasing from a negative infinity to -1.8. Remember the x's? Sorry for writing so scratchy. And then 5.2 to infinity. And then it's in between those two for the other interval of increase. Just double check that. Yep, from -1.8x to 5.2x, you have that chunk that's increasing. All right, and then I'm going to skip to the third one. Who has only an interval of decrease? That's what that means. It's decreasing from negative infinity to positive infinity. What number is that? 2, 3, 4, 5, or 6? It's 5. So we're looking at this one. And I do want to focus on that. That's like our one of the ones that we graphed today. There's just a little flattening out, but that does mean the graph continues to decrease after that flattening out point. That's called a point of inflection, by the way, right there. Right, and that makes that different than a linear function. You know, these x to the thirds that have that. So what's easy about this is there is no interval of increase or decrease. Well, I'm sorry, there is no interval of increase. There are no relative minimums and maximums because there is no change in direction from increase to decrease or decrease to increase. So that's nice and that's easy. The intercepts, what do we have here? Oh, a coincidence. We have an x-intercept and a y-intercept, the same numerical value, but different, as far as the coordinate is concerned. It's a nice little homework question. We just don't have the time to break down all the other ones and all these other different attributes. We got to move on and get some different things going on here. Okay? All right, so a couple of those, good enough. We don't get a chance to do this and don't have time. But you can go ahead and kind of plug in your calculator if you wanted and play with this stuff and see how it changes things. As far as this is concerned, this is exactly like intercept form when we had parabolas. When it was squared, this told me where the vertex was. Do you guys remember that a little bit? All right. Well, I'll tell you how you should remember it when we go to the chart. Input, by the way, but oh my goodness, are you okay over here? All right, so that's what this is. This is like in transformational format. Don't use your calculator. As a matter of fact, we are probably going to have you do this on a no calculator part. Be able to graph this. Notice what's right in the center of my chart of values. Y negative 3. Well, what's negative 3 plus 3, everybody? Say it. 0. What's 0 cubed? 0 minus 4 is? This is the point of inflection. This is the most critical point for this cubic. And I think I know from the last, we don't really have to change the scale on y. I think all these points kind of come close to making it. But that's where we're going to get this flattening out of this graph, right? And that's why that's important. And that's why if you had to create your own chart of values, you would put negative 3 right in the middle of your chart and then do 2 above and 2 below at least. All right? And that's the truth. So I could do this in my head. What's negative 4 plus 3? What's negative 4 plus 3? Negative 1 cubed is what? Negative 1. Okay, you have a negative left over. What's negative 1 minus 4? So input, say it. Output, negative 4, negative 5. Remember those fun days? All right? No, I shut that out of my head. Negative 2 plus 3 is what? Negative 2 plus 3. 1. 1 cubed. 1 minus 4. Negative 3. Be careful. Okay? So it is that. All right, so expectations that there's that. Okay, well, it looks like a linear function right now. Right? It's not until you plug in the next points. Negative 5 plus 3 is negative 2. What's negative 2 cubed? Don't forget about a negative cubed. Negative 8. What's negative 8 minus 4? A negative and a negative is a bigger negative when you subtract. Okay, so this one's off the charts a little bit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So negative 5, negative 12 just kind of comes, it's off the charts there. Okay, not linear. And then negative 1 plus 3 is 2. 2 cubed is 8. 8 minus 4 is 4. Won't bother you. But then it's interesting. Negative 1, 1, 2, 3, 4. Watch what happens with 0. 0 is not as fun when it's in this format. So we got a little calculation here. 0 plus 3 is 3. What's 3 cubed? 27. Minus 4 is 20. Well, I can't think. 23? Oh, man. I don't know if I put that. I think I did. Ay, this is way gone. So this graph has actually taken off, man. And there it is. It flattens out there. There's that point of inflection, right, that I want you to know. And it doesn't even hit the y-axis till 23. So I got to show that it doesn't hit the y-axis there. All right, so there's what I'm talking about there. I think you can handle graphing that then. You shouldn't have to be supplied with those values to the left there. You should know that you start with negative 3 and then go up and down from there. All right, so domain and range, it's the same. All cubics are going to look like this. When we get to fourth powers, fifth and sixth, then we got to watch it. All right, so on and so forth. Easy, because I don't have a minimum or maximum. And therefore, I only have an interval of increase. So getting used to this stuff for today's situation. No interval of decrease since it increases forever. The y-intercept, we luckily had it in our chart. If we didn't, you just have to plug in 0 for x and calculate. And it could be an enormous number. You never know. Then the end behavior, you'll get redundant with this. It's pretty simple. I'm not even doing number 2. We got to move on. I think the point's been made. The limit of f of x as x approaches negative infinity. That is negative infinity. Limit of f of x. What is y approach? Whoops, that's not a line. I don't know why I did that. That was a Samuelus brain misfire, a synapse misfire. All right, as x approaches infinity, so does y. Okay, so I don't think we have to do this one. What we would see on this, though, which way would it go? Would it be in the same direction or would it be opposite? Opposite. You'd end up like this and end up down like this, and you have something like this. Something along those. It actually wouldn't have that loop in the middle because this is you know, uh, a shifted format of this one. That's why you'd plug in 1 first. 1 minus 1 is 0, and then go from there. Ooh, then you remember that good old days of quadratics and intercept form? Ah, this is intercept form. This is very simple. So what would I plug into my chart? The intercepts, the x-intercepts. Why is -4 an x-intercept? What's -4 plus 4, everybody? 0. What's 0 times this, times this, times that? I didn't get those numbers, but 0 times anything is what? So as soon as I plug in -4, I get 0 as an output. That is why this is an x-intercept. For those that didn't get that back in the day, I didn't know what was going on. I know there's a lot of goofiness, though. We know that for a fact to not get this figured out. 3 minus 3 is what? 0 times 0, 0 times whatever, times whatever, times whatever is still 0. So when I plug in 3, I get 0 as an output value. Plug in 1, I get 0. Same old, same old. So I'm going to start with graphing those. 1, 2, 3, 4. 1, 0, and then 3, 0. Okay, there's my x-intercepts. Then you're going to find out, you should know how this graph is going to look. It's all about the end behavior. How is it going to end? Is it going to end going straight up or straight down at the end? Up. So we'll be able to graph these through x-intercepts, and you could get at least a decent shape of it. But we'll go ahead and plug in these points. Watch how I do it. It's very easy. What's -5 plus 4? So just put -1 here with a pencil and then be ready to erase it for your next thing. What's -5 minus 3? That's a big one. -8. And then what's -5 minus 1? Yikes. And then it's half of that. That's 8 times 6 is 48. A negative times a negative times a negative is a negative. So half of -48 is -24. Okay, I think I am going to go by twos, but even in going by twos, 2, 4, 6, 8, 10, this goes to -20. So -5 comma -24 is still off the charts. Just want to make sure I got that in the right spot there, somewhere down there. Then I think I screwed this up. I might have plugged in -3 on accident. And I'm not sure why the chart has -2 there. Maybe just because it's 2 away from 0. I don't know. But let's just plug in -2 now. What's -2 plus 4? Ooh, man, somebody's excited back there. What's -2 minus 3? -5? Oh, I need an answer now. And then what's -2 minus 1? I think I did do this one. -3. Maybe I did make the mistake. So -2 and then half of that. That's positive 15 times 2 is positive 30. Half of that is 15. So no rhyme or reason why we went to -2 for that. 2, 4, 6, 8, 10, 12, 14, 15, I think right around there. Hopefully I counted right there. And then we have that picture. There's gonna be something better than doing this, but this is just getting a ballpark. So if I supply the chart, just go ahead and follow along because I am gonna have there is a relative maximum and minimum. Is it technically at -215? We'd have to use a calculator. There's a feature to find it exactly. We're gonna ballpark it and say it is. Because when I plug in 0, this starts going back down. 0 plus 4 is 4. 0 minus 3 is -3. 0 minus 1 is -1. And then I take half of that. That's -12. 12, half of 12 is 6. 2, 4, 6. So there's the y-intercept. So that was 6 there. 2, real quick. 2 plus 4 is 6. 2 minus 3 is -1. 2 minus 1 is 1. Half of -6 is -3. That's there with my scale of 2. I didn't mark it, but, I don't have time. And then 4, it's going to be probably a big one. That's the point of this taking off. 4 plus 4 is 8. 4 minus 3 is -1. 4 minus 1 is 3. Did I do that right? 4 minus 3 is +1. What am I doing? 4 minus 3 is 1. All right, and then half of that. So not too large. It's 12 because 3 times 8 is 24. 4, 2, 4, 6, 8, 10, 12. Now when I mark these up, what am I talking about? When I connect the dots, then we do get that curvature that we expect, the roller coaster of an x to the third. You can imagine if I plug in 5, 6, 7, those y values start going nuts. This is not going to come back around. This is going off to infinity as I plug in big x's. So again, the domain range, not a big deal. We'll see this change when we have x to the fourths. There is some issues. Now, ballpark. We should actually go to the graphing calculator and type this and find the actual maximums and minimums. But from the points that I have here, -2, 15, 15 is a relative maximum. So we will say 15, I almost put that in the wrong spot. I did last hour, then I shoved it over. At x equals -2, that's the only one that I see right now. And then a relative minimum, the one that I see is 2, -3. So relative minimum is -3 at x equals 2. And then I do have a bunch of increasing and decreasing based off of those x values. So from negative infinity to -2 when we get up to that 15, and then from 2 to infinity. And then the decrease is between those two values. So from -2 to 2, we have that those x values create that decreasing y behavior. Just kind of wanted to mark that last one there so you understand that. Luckily, I don't have to write the x-intercepts again. You could just arrow those over here. But the y-intercept, that's also on our chart. That's 0, 6. Just don't feel like doing it. And then I'm good on the limits because I want to move on to the next stuff. What time is it? What time did we get out of here? 25? 27? So I have 9 minutes. Maybe we are done here. Maybe I won't be lazy then. But we see the x-intercepts. But limit again. As x approaches negative infinity. I guess this is where we stopped the other hour. That was not the pen. I think I just lifted that off the screen. Actually, the pen wasn't too bad today, huh? Didn't sabotage me too much. I didn't have to throw a fit. By hitting it on the kid. Well, it just happened. Oh. So right when I compliment you, pen, you backstab me. All right, and then it's more of the same. What can we expect for the end behavior on this though? Would it be the same or flipped? It's the opposite. So this would end increasingly down. Notice what's on there. We got 5, 0. We got -4, 0, and -1, 0. Those are x-intercepts for sure. All right, and then you can do that on your own. We definitely did stop here. I'm going to stop with you guys, and we'll call it a day. That second set of notes will hit tomorrow. Okay. All righty.